inorganic substances. So also, before I start with this, if you see me looking here at any point, that's because my monitor is here and that's where the slides are in big letters, and here is the camera. So I will be like, we'll work it out. But yeah, so here is the syllabus for inorganic substances. The main inquiry question is, how are the ions present in the environment identified and measured? So basically, you can break this down into 3 parts. The first part is monitoring the environment. This one's a really easy one. You just have to be able to articulate why we need to monitor the environment. Then the second one is qualitative investigations. This is figuring out what cation is it, what anion is it, based on primarily 2 things, the flame test and precipitation, but also complexation, which is a little bit tricky, but we'll get to that later. And then the last part is quantitative investigations, which is your gravimetric analysis, your precipitation titrations, colorimetry, UV, Biz Spec, and AAS. So quite a lot to cover in this first inquiry question, but as you go through it, you'll see that a lot of it is stuff that you've heard of before, or just pretty self-explanatory stuff. So an example of the self-explanatory stuff is monitoring the environment. So this one is a pretty easy dot point to check off because it's a lot of common sense. So we need to monitor the environment because the environment is very important to both human health, also the health of different parts of our ecosystem. So for example, waterways, we need to make sure that they are not getting bombarded with toxic chemicals from nearby factories. We need to make sure that that water is still drinkable for resident wildlife and still usable for watering the crops that are grown in those nearby areas. So that's why it's important to monitor water levels, toxin levels in water. And yeah, just to prevent a buildup of toxic waste. So an example is lead. There was an issue in Japan where there was lead in waterways, got into the fish, and then when cats ate the fish, it caused the cats to have symptoms of lead poisoning because there was lead in the system of the fish. So it's just a cycle, basically. It interrupts how our ecosystems work. So it's really important that we prevent that buildup of toxic waste in the first place, and how we do that is by monitoring the environment. And then the other main example is the atmosphere. Again, it's pretty common sense because the atmosphere is the air we breathe, and we don't want the air that we breathe to be toxic for obvious reasons. But buildup of toxic chemicals not only can make it difficult to breathe, but can also cause acid rain, which has a bunch of other issues, not only for like humans, but for, again, like environments and plant and animal life. So it's very important that we monitor the atmosphere, particularly carbon monoxide and lead. So lead from leaded petrol, it can send, burning of leaded petrol can send lead particles into the atmosphere. And when that happens, if there's a buildup of lead in the atmosphere, we could get lead poisoning from just breathing, and we don't want that to happen. Lead poisoning is not fun for anyone, so that's why we need to monitor the environment. Basically, this whole dot point is just you being able to go, if we put toxins in vital sources of life, so water is very key to life, air is very key to life. If we put waste in that and put toxins in that, it's obviously going to have very negative impacts. So that's basically all you need to be able to say on this one. Another thing that comes under this is eutrophication. This one is a process that is really good to remember, just because it's very relevant and very easy to remember. Like it's while it is memorization, it does follow a very, very logical process that makes it super easy to remember. So first, what happens is that fertilizer runs off into waterways, and the nutrients from this promote algal bloom, that is the green stuff that is on top of the water. And then what happens is, you can see in that photo that the green stuff is quite dense, quite thick. So basically, we need to make sure that that doesn't happen, because if that does happen, then that blocks the sunlight from going into the water, and it prevents the plant matter in the water from being able to photosynthesize. When it's unable to photosynthesize, that plant matter dies and the decay uses up oxygen. The other thing about photosynthesis not occurring is that when photosynthesis doesn't occur, oxygen isn't being produced in the water, which means that there's less oxygen in the water from both decay and lack of photosynthesis, and therefore a lack of oxygen for the animal life in there, which causes like the fish to die, any other animal life in there to die. So it basically ruins the whole balance of that ecosystem. So it's super important that we monitor fertilizer levels, not just toxic chemicals in our environment. So that's basically the first dot point of the syllabus done. Moving on to the qualitative investigations, identifying cations and anions. We'll start with cations. So there are 3 ways that you can identify cations. It's the flame test, the precipitation reactions, and also complexation. For flame tests, really all it is being able to memorize the colors that go with what cation. So on the left, we have a list of the cations we're supposed to know, and so supposed to be able to identify. And then on the right, we've got some of the main colors. So barium is apple green, calcium is brick red, lead is white. Lead, I don't know if you've done a flame test before. You should have done one, but just like a side note about lead, if you're using an example in your exams, you should never use lead flame test as an example, because you should not be doing that in a classroom setting, because lead is toxic, as we know, and if we're spraying around lead or having lead just out in the open, it's not good. So when we're using flame tests as an example, we should use something like copper or calcium or barium or iron, not lead. Anyway, that's a side note. Copper has a blue-green flame, iron is a yellow flame. So whether you got a solid, put it on a little bit of one of those loops and then put it over the flame to get the color, or you sprayed a solution of it through a flame to get the color, in both ways, lead should not be used. The rest, it's fine to use them as an example, but basically just know those colors, know those ions, and that's basically all I could tell you about the flame tests. But yeah, just know the colors. That's really all that you can do for that. So for precipitation, you need to know your solubility rules. So solubility rules, they come up everywhere in a whole bunch of questions. So it's very important that you know them, and how I remember them, and how I think a lot of schools teach you to remember them. It's NAGSAG. So NAGSAG is for nitrates, ammonia, group 1, sulfates, acetates, and group 7. And then for sulfates, they're all soluble except for calcium, strontium, and barium. So how my teacher told us was castrobar, however you want to say it, that's for sulfates. Those are the exceptions for sulfates. And then PMS for the exceptions for group 7. So group 7, they're all soluble except for when they're with PMS, which is lead for PB, magnesium, and silver. It's Ag, but S for silver. So in summary, cations, all group 1 is soluble, castrobar are not soluble with sulfate, and PMS are not soluble with group 7. So if you just know the solubility rules and know their exceptions, precipitation is really, really easy, and it should come just naturally. Once you do lots of questions, you'll know the common ones that they like to bring up. So a lot of the time they like to bring up barium sulfate. I don't know why, but barium sulfate comes up a lot. And yeah, so just the more you practice the questions, the easier it gets. So we'll do a little bit of practice. So predicting whether these will be soluble following the solubility rules. So silver chloride is a group 7, so they are all soluble except for when with lead, magnesium, or silver. Since this is silver chloride is insoluble, so it would form a precipitate. Barium sulfate, I kind of said this before, but sulfates are all soluble except for when they're with calcium, strontium, or barium. This is with barium, so it's insoluble and will form a precipitate. Calcium chloride. This is a little bit tricky because if you remember the exceptions, but you get them mixed around, you might think that calcium, when with group 7, produces a precipitate, but it does not. Calcium produces a precipitate with sulfate, but not group 7, so calcium chloride is soluble. Lead chloride, on the other hand, is insoluble because lead is the P in PMS, that is the exceptions to group 7. So that's that. And then iron nitrate, iron 3 nitrate. Nitrates are all soluble, no exceptions, therefore iron nitrate is soluble, no precipitate. So that was a little bit of the thinking process when you go through it. So just go through your NAGSAG. If it helps, you can, whenever you have a precipitation kind of question, just write NAGSAG somewhere. It will probably jot your memory and help you remember what your solubility rules are. But yeah, just know them and you're all set, and they'll be pretty easy from then on. So complexation is another way to identify a cation, and most of the time it comes with a very drastic change in color, and that's what identifies whether it's there or not. So for example, if you have a solution of iron, and let's say it's pale yellow, which it usually is. You have a solution of iron, and then you add your thiocyanate. Complexation reaction occurs, and this causes it to go blood red because of complexation. So that's an example that you should have seen in Module 5, iron thiocyanate, and that complex. But basically, complexation as a whole, it's when two substances react to form a complex. And in my head, how I remember it is there's an X in complexation, so it kind of looks like an X. So it's like a one central one with like an X around it. That's how I remember it. Sometimes there's like 6 or 8, not 4, around the cation, so it doesn't look like an X, but usually there is. So there's some sort of like a cross over like a central cation. So that's just how I remembered it. It's a bit silly, but you know, whatever gets you to remember chemistry, it works. So yeah, you don't see this a lot in the HSC, but if it were to come up, most of the time it would include water, ammonium, or hydroxide. Or, like the example I said earlier, iron thiocyanate, because that's something you should have encountered in the past modules. So it goes from that pale yellow, clearish color to blood red. And that's how you know that complexation has occurred, and that's how you know that there are iron ions in the solution. So that's one way of identifying it. So now to anions. Precipitation follows the same things as the cations in terms of the solubility rules. You just go through the solubility rules and you should have some type of answer to what anion it is. But some other bits and pieces to remember are that carbonates and phosphates are insoluble, and hydroxide is insoluble, but with the exception of calcium and barium, which are sparingly soluble. So that's the only extra piece of information you need to know other than the solubility rules. Everything else you can figure out with just the solubility rules. So another thing is, we'll see this in another slide, but if you have a carbonate ion, it will react with acid, because if you remember from year 11, acid-carbonate reactions produce carbon dioxide. So what will happen is, if you have a carbonate, a test to figure out if it's a carbonate is you add an acid to it, and it forms bubbles, and those bubbles are carbon dioxide. But we'll get to that. So, for flowcharts, a lot of questions when it comes to identifying ions, it requires thinking like a flowchart. So it's like the process of elimination, basically. So you start with something, and then if it does this, so let's say you start with all the cations in a mix and you add chloride, then you can have a precipitate form with lead or silver. Then when you're choosing between those two, what you can do is put the precipitate under UV light, and then silver will decompose, so that if it doesn't decompose, you know it's lead. If it does decompose, you'll know it was silver. So that kind of thing. If you add sulfate, barium and calcium precipitate, and then you can distinguish them based on the flame test colors. So it's like you narrow it down, and you narrow it further and further down using a bunch of different tests until you have only one possible ion. And sometimes you'll be required to draw up a flowchart of how you'll find that final ion. So it's good to know all of the options that you have. So if you add hydroxide, magnesium, iron, and copper form a precipitate, and this is where it's important to know the colors of the precipitates. Most of the time, it's similar to either their flame test colors or it's very distinct. Most of the time in the HSC, if you do need to know the color of the precipitate, it'll never be like a white precipitate. Well, it could be, but they'll give you enough information so you don't have to just know the color of the precipitate, if you know what I mean. So for example, lead iodide is a bright yellow color. That bright yellow color should immediately let you know that it's lead iodide. But if it's magnesium hydroxide, which is white, barium sulfate and calcium sulfate are also white. So they wouldn't give you something where there's lots of options. They'll give you something where there's only one option. So it's just something to think about when you're stuck with a question. There's only one answer, really, so you just have to keep doing stuff to figure out what it is. So, for example, if you have 3 white precipitates, maybe all of them give a different color in the flame test, stick them in a flame, and that'll give you your answer. So it's just those kinds of flowchart questions. Anyway, back to the slides. Magnesium hydroxide is white, copper hydroxide is blue-green, and iron hydroxide is white but oxidizes to green, and iron 3 hydroxide is yellow-red. So they all have different colors except for the 2 white ones, but one oxidizes to green. So in that situation, you'd oxidize it. If it turns green, you'll know that it was iron 2 hydroxide. If it doesn't, you'll know it's magnesium hydroxide. So a bunch of different options there. And the same with anions. As I said before, the thing with acid carbonate reactions produces CO2 bubbles. If you react it with copper, a blue precipitate will form with phosphate, and a blue-green precipitate will form with hydroxide. And if you can't tell the difference between blue and blue-green, I get it, because it is a little bit hard to tell. But another thing is, if you react an acid with a hydroxide, it'll be more vigorous than an acid with a phosphate. So you can just see for yourself. For barium, it'll form a white precipitate with sulfate, and lead, as I said before, a yellow precipitate with iodide, white precipitate with chloride or bromide. And then, if you're choosing between chloride or bromide, there's a cream-colored precipitate when added to silver when it's bromide, and then silver chloride is white. So again, you just need to just keep adding stuff until you narrow it down to one last one. So we'll do a couple of questions. This first one, if we read it, the student finds an unlabeled beaker. It's left over from a previous crack, so they deduce it must possess carbonate, sulfate, or chloride. They add nitric acid, they don't observe bubbles, then they add barium nitrate, and they observe a white precipitate. So, if we use the logic of process of elimination, it cannot be carbonate, because if it was carbonate, it would react with the nitric acid to form bubbles. Then that leaves you with either sulfate or chloride. That's when you go to your solubility rules, because it says that a white precipitate was formed. That white precipitate has to be either barium sulfate or barium chloride. If you remember from the solubility rules, you'll know that barium chloride is soluble because it's a group 7, and barium is not one of the exceptions. So it has to be a sulfate anion. There you go. That's how you figure out a question like that. So I eliminated it until there was only one left. That's how you should approach those questions. For this question, it's really just knowing your solubility rules. It looks a bit complicated, but really all you have to look is at the end of step 3. So iron chloride is added to sodium hydroxide to form a brown precipitate. So if we look at the reaction, iron chloride plus sodium hydroxide will make iron hydroxide, or iron hydroxide and sodium chloride. So we know sodium chloride is a group 7 anion and a group 1, so it's soluble. And we know that iron hydroxide is a hydroxide, which is insoluble. And iron is not one of those exceptions to hydroxides being insoluble, so therefore the brown precipitate has to be iron hydroxide. So again, just the process of elimination and using those solubility rules to find that final answer. But yeah, so that's that. So that finishes up the qualitative investigations, and now we're on to the quantitative investigations. So this is not just identifying, but being able to measure. And for gravimetric analysis and precipitation titrations, I'm not going to talk about them much because gravimetric analysis you should have done in year 11, and precipitation titrations follows the exact same process in calculations as normal titrations. In precipitation titrations, there's a bunch of different methods that you can use to do a precipitation titration, but generally the endpoint is where there's no more precipitate being formed. So when you approach these questions, it's really important that you're good with basic moles calculations, because that's where most people would go wrong in this situation. Not knowing your moles and not being careful of balancing your chemical equation at the beginning to make sure that all your ratios are correct. I think the most important thing in chemistry is writing down the equation to start off with, because that can help you avoid so many mistakes along the way if you have a good balanced equation at the beginning. So yeah, gravimetric analysis is determination of an analyte based on mass, and then precipitation titration is based on when that endpoint is reached. So just know your moles, just be very careful with those moles when you do the calculations, otherwise they're very simple. And it's something you've done before, so I won't go over that. So another way that you can measure is colorimetry, and the main way that you will see this come up in the HSC or in your trials is as a calibration curve. Either you having to draw one and then look at the absorbance for a sample, or just find out the find out the concentration based on the absorbance. There's lots of different ways, but it almost always ends up with you reading a calibration curve. So I'll talk about that more in a second, but just some theory behind it. It's based on how intense the color is. So some more theory behind it is just that when energy is added to the atom, it excites the electrons, and then when it goes back into its ground state, it emits a photon, and that's color. And when it emits that, it means when it emits more of that, it basically means that there was a higher concentration. So the more energy it emits, the more concentration it has, and that can help us figure out what the concentration of something is. So basically, that's the theory behind it. I'll go straight into how it will come up in the HSC, and it's just a calibration curve. So key things to a calibration curve is that it needs to be precise when you're doing when you're making like the standard curve. So you use known concentrations, find out their absorbance, and then plot it. and then you should get a pretty straight line if you're super precise. And when it's really straight, you can have an equation for the line if it's there in your question. That's really good because it makes it really easy to find out concentrations based on absorbance. But if not, the standard way to approach this is you get your absorbance. Let's say it's 0.3. You just draw a line across until it hits the line, and then you draw a line down, and it hits the line again, and then you read off the concentration. So basically, that's all there is to colorimetry, just being able to read off that graph or use the equation of the line to find out your absorbance or your concentration. That's really all you have to do for colorimetry. Now, UV Biz Spec is a little bit tricky. It doesn't come up much. It did end up coming up into my HSC, which was quite unexpected because I was told by everyone, oh, it probably won't come up, but it will. It will if you're not prepared, so be prepared for it, just in case. It's very similar to colorimetry, but how it works is that it measures the wavelengths of light absorbed by a certain compound, and this corresponds to certain bonds. And all that information is on your data sheet, the bond stuff, but how it came up into my HSC was this question here. So it says which wavelength would be appropriate to determine the concentration of Q in a mixture of two solutions. Basically what you're looking for is a place where the solution Q has a high absorbance and solution P has a low absorbance. The two areas where this happens are here and here. So 475 and 630, which both happen to be options in the multiple choice. Basically what it comes down to is that we want 630. That's the correct answer. D is the correct answer because you'll see that P does not have any absorbance at that wavelength, which means that we know for sure that everything being absorbed at that wavelength is being absorbed by Q, which means the concentration that we will calculate will be the concentration of just Q, nothing else. If we do it over at 475, some of it is being absorbed by P, so we'll have a number that is much higher than the actual concentration because we think that the little bit that's being absorbed by P is actually being absorbed by Q. So that's why we need it to be 0 for P and then high for Q. So 630 D, that's the answer to that question. So another part of UV Viz Spec is the Lambert Law. This is a little bit of a weird part of the syllabus, I'd say. It doesn't come up often, again, but it's still worth knowing. The equation is on your formula sheet, and it looks exactly like that here. This is just on the top of your formula sheet, and what you need to do is just plug in the numbers, basically. So knowing what everything stands for, you got your IO, which is the initial light intensity, and the I is the final light intensity. So that intensity is after a little bit's been absorbed by whatever is in the cuvette. Then the funky E looking thing, I don't know what it's called, but it's the molar absorptivity, and the L is the length of the cuvette, and C is the concentration of the solution. So you just need to be able to plug in the numbers, and it's really easy from there. So an example, a red solution has a molar absorptivity of 2 liters per mole centimeters. If a light passes through 4 centimeter wide cuvette and has an absorption of 6, what is the concentration? So yeah, you'll have to work backwards because in this case you have the absorbance and you want to find out the concentration. So here's the solution. Absorbance is basically the 2 times the 4 times the mystery concentration, and that absorbance is equal to 6. Then 6 on 8 simplifies to 0.75, so the concentration is 0.75 moles. So that's basically how you use the Lambert Law. You can also use it with the light intensity stuff, but I didn't have a practice question for that. So just know that if we go back, just know that the incident light is what goes on top and the transmitted light goes below it. So that's really all you need to know. Yeah, so we'll move on to AAS, so Atomic Absorption Spectroscopy. And this is similar to the other methods that we've been discussing already, colorimetry and UV Biz Spec. And it's determining the concentration of a compound based on the light absorbed or emitted, and it's very useful for trace elements, very small concentrations. So use it a lot for like figuring out if there's too much of toxic chemicals in the environment, because usually it's very small concentrations that make a very big impact in the environment. So the steps that it involves are, first off, the sample is vaporized, and then once it's vaporized, it has a cathode lamp light shone into it, and this goes to a detector, and this determines the amount of light absorbed by that vaporized substance. Then after this, it goes into a computer, which does all the tricky stuff. It just compares the absorbed light with the standard curve, and then it allows the concentrations of ions to be determined. So really the main steps is first it being vaporized, and then second the light being shone through it, and then third the detector. So those are the key things that you should remember for the process of AAS. That's what it looks like. So you've got the hollow cathode lamp, you've got the vaporized substance, you've got the monochromator and the detector, and then the computer, which does all the data processing. Okay, and then some examples are, or some examples of where it's been used is in South Australia to identify regions that were lacking in cobalt. And yeah, so basically it's just used to find and monitor trace elements, very small concentrations. If the concentration is too small, it won't show up, but like this can do pretty small concentrations. So it's good for finding those small concentrations. An example of putting all of this together is this question. So this is one of the sample HSC questions from NESA, and it uses complexation as its main thing, I guess. So if you look at the question, I'm going to read it, I guess, because I don't know. A colorimeter was used to calculate the percentage of iron. Tablet was dissolved and oxidized. That's the reaction. The resulting solution was made up to 200 milliliters with distilled water. Absorbance was 0.6105. That's a calibration curve. How much iron was in that tablet? Now, this would have sent me into a panic if I was in the HSC, because there is so much information being told to me. I've got some reaction that looks like complexation. I have 200 milliliters. I have an absorption. I have how much gram the tablet was originally. And then I've got this calibration curve. It's quite overwhelming, all of the stuff that's on the screen. But if you take it step by step, it's actually quite simple to figure out what's happening here. So the first thing that you would need to do is check that the equation is balanced. It is balanced, so you're all good to keep moving on to the next step, which is to ignore the 200 milliliters with distilled water for now. Just because that's something that comes up later. If you worry about it now, you're going to forget the main part of this, which is reading that calibration curve. So they were kind enough to give an equation for the calibration curve, and that is y equals 0.0111x. So if you use the absorbance, which is 0.6105, and you multiply and you divide that by 0.0111, you'll find that the concentration is 55. So it's 55, I want to say micromoles. I think that's, yeah, micromoles. So 55 micromoles, and we want it to go into moles just because it's so much easier to deal with moles than it is micromoles. So then what you need to do is convert it to moles. And how you do that is move the decimal place back, and then once you have it in moles, you want to put it into the 200 milliliters that it's in. So it's micromoles per liter originally, and then once we convert it to moles per liter, we want to find out the actual number of moles. And how we do that is by ignoring that 200 milliliters and using that to find out the number of moles. So we times it by 0.2, and then once that happens, you can multiply it by the molar mass of iron, and that should give you an answer. So it's a little bit blurry, but we'll deal. That was basically how I did it. I talked through it all just then, but written down, it kind of makes more sense. But yeah, so the important parts to remember for this type of question, when there's so much information, is keep in the back of your mind how many milliliters it was in. So in this one, it was in 200 milliliters. You don't want to be going on with the question assuming that it's in 1 liter when it's in something smaller, because that can lead to a completely different answer. So don't disregard that, but don't worry about it straight away. You'll see that I only used that in the second part. If I used it right in the first part, I would have gotten confused, something would have gone wrong. So it's very important that you deal with the absorbance first, and then you deal with the moles, just like I did here. So the answer in the end happened to be, what was the option? C. It happened to be C. So for those types of questions, just be really careful with your moles, and if you're doing any type of making it from millimoles to moles or micromoles to moles, just be really careful with your decimal places there. But yeah, that was one of the sample questions, and once you go through it, it's actually much easier than it looks. So some more practice questions before I move on to the next question. Basically, first, which of the following could not be used to determine the concentration of an ion? The answer is flame test, because flame test does not tell you anything about the concentration of an ion. It only tells you what ion it is. So that is the flame test. Question 2, which of the following will form a precipitate with sulfate? If we look at all of them, only one of them is from the Castro-Bear exception, and that is barium. Like I said earlier, barium sulfate is one that they love. They love using barium sulfate. Who knows why? But yeah, so barium, C. And then for question 3, which of the following might be a useful way to check if iron 3 is in a solution? And this goes back to complexation. So if you remember my example before, iron thiocyanate, that complex, that goes from a pale yellow solution to a blood red one, and therefore option F, it's not A, B, C, or D apparently, it's option F. Option F, add thiocyanate, is the correct answer for that question. So that's basically all of that first inquiry question. And now we'll